Hello students, good day. I hope all of you are safe. Today we will start a new section in the operating system course, and that is memory management. As all of you are well aware that the first step to start the execution of a process is to bring that process into the main memory, the RAM. So conceptually, this should be the first unit that one should discuss in the operating systems course. However, because discussion of this module requires some other concepts as well, that is why in the sequence it is at the third position. So we discuss it after CPU scheduling and after synchronization and various issues that are associated with it. So today we will start the unit of memory management, where we will discuss that how a process can be loaded onto your main memory and what are various aspects that are associated with this process. To start its execution, a process has to be present in the main memory. As the main memory and the registers are the only storage that the CPU can access directly, so a program that is stored onto the hard disk has to be loaded onto the main memory so that it can get executed. Usually, we categorize memory with respect to the access time that the CPU may take in order to fetch data and instructions from them. So in this regard, registers are the fastest memory available to the CPU. Then we have the cache memory followed by the main memory. So after these three memories, then we have after having a huge difference of speed, we have our hard disk and then some other peripheral devices. One of the primary goals of this memory management unit is to ensure that multiple processes running in the system should not interfere with each other. To achieve this goal, we have several mechanisms in place. One of these mechanisms, and a very basic one, is the use of the base and the limit registers, which store the starting and ending addresses on the main memory, which a particular process may have access to. So when there is a request for a memory access from a particular process, the CPU must ensure that this access request falls under the limit of this base and limit registers. So over here we have an example. So you can see that this is our main memory, and your operating system is already loaded onto this main memory, and over here we have several processes loaded onto this main memory. So for a particular process, that is this P2, we have a value in the base register and we have a value in the limit register. So whatever access request is generated by this process, the CPU will ensure that it falls under this base and limit register. So over here we have the hardware address protection through the base and limit registers. So you can see that any address that is generated by the CPU, it should be greater than the base register and it should be less than the limit register. And if the address satisfies this criteria, then it will be given access to the main memory. Otherwise, we have a trap to the operating system that this is an address that is not allowed to be accessed by this process. A program that is stored onto the hard disk is a collection of instructions, and those instructions, they have some numbers, or you may call them addresses, which are relative to that program. So a program that is stored onto the hard disk, it has some instructions, and those instructions have some addresses relative to that program. Usually we call those addresses as the logical addresses because they are only meaningful within a program. So they are logical, not physical addresses. And when that particular program is loaded onto the RAM, onto the main memory, then those instructions, they have to be stored somewhere on the main memory, on some particular address which is physical. So there are physical addresses onto the main memory where those logical addresses have to be loaded. So this mapping of logical addresses onto the physical addresses is termed as the address binding. So we have logical addresses in a program and we have physical addresses onto the main memory, and we want to load those logical addresses onto those physical addresses. So this mapping of logical addresses to the physical addresses is termed as address binding. However, to have this mapping, we require some support from the operating system, as it is very convenient that the same logical addresses can be mapped onto the same physical addresses. So to have multiple processes that are present in the system at different locations onto the main memory, we require some support from the operating system. If we have multiple processes running in the system and they may have the same logical address space, then if the very intuitive scheme of loading them onto the same physical addresses may end into having multiple processes loaded onto the same location on the main memory. For that reason, we require some support from the operating system so that different processes can be loaded at different locations on the main memory. This mapping of logical addresses to the physical addresses can happen at different times. For instance, when we are compiling our code, if we already know that a particular logical address will be mapped onto a particular physical address, then we can perform this binding at the compile time. However, to achieve it, we require some information beforehand to have this mapping at the compile time. Another possibility is we can perform this binding of logical addresses to the physical addresses when we are loading our program from the hard disk to the main memory. So if we do not know the physical addresses at the compile time, we can delay this till the time when we are actually loading our program from the hard disk to the main memory. And then the third possibility is that we can delay this binding of logical to physical addresses till the time when a process is in execution, and we call it as execution time address binding. Over here we have the formal definitions of the logical address and the physical address. So logical address is an instruction number that is seen by the CPU, and it is relative to the user's program, while the physical address is a memory location on our main memory, and that is the address as seen by the memory management unit. Likewise, the logical address space is a set of all logical addresses that can be generated by the CPU, while the physical address space is the set of all physical addresses that are present onto the main memory. This physical address space is about the size of the main memory, while the logical address space relates to the size of the instruction that the CPU can generate. Usually when we have discussion about 32-bit architecture and 64-bit architecture, we refer to the size of the registers that are present in a particular architecture. So in a 32-bit architecture, the maximum memory location that can be accessed by the instruction register is 2 raised to the power 32, which is equivalent to 32 gigabytes of memory. So when we have a 32-bit system, we cannot access a memory that is greater than 4 gigabytes, which means that there is a restriction on the maximum size that a program may take in a 32-bit system. As we have discussed earlier, that one of the primary aims of this memory management is to map the logical addresses to the physical addresses. And to achieve this goal, there are several possible methods. One of the primary method is to use a relocation register. Now, this relocation register contains the value of the minimum physical address that is allocated to a program. So the minimum physical address from where a program is stored onto the main memory is stored in this relocation register. And when the CPU generates an address or generates a request to access a particular instruction in that logical space, the logical space address is added to the value of this relocation register to generate the exact location of the physical address where that corresponding logical instruction is stored. To completely grasp this concept, let's consider an example where we have 5 processes running in a system. So each of these processes, they have their logical address space starting from 0. However, even though that their starting logical address is 0, they are mapped onto different physical addresses onto the main memory. So now let's suppose that the first process, process A, has a logical space that starts from 0 and goes up to 150 hexa. However, its physical address space is from 2000 to 2150 hexa. So these logical addresses are mapped onto these physical addresses. However, in the same manner, if we have another process, process B, and its logical space is the same, 0 to 150 hexa, it is possible that on the main memory, its physical address space is from 4000 to 4150 hexa. So which means that this logical space is mapped onto this physical space. So for the relocation register of process A, the value will be 2000, and the relocation register of process B may contain a value of 4000. So here we have the modified architecture to map the logical addresses generated by the CPU onto the physical addresses that are related to the main memory. So once a CPU generates a logical address, it is just checked against the lower limit that a process can access, and then the value of the relocation register is added to the logical address to generate a physical address in order to access the memory, the main memory where the instructions and data are stored. All right, so moving on, we have the next concept of overlays. But first, let's discuss the challenge, which is a motivation to this concept. We already know that in order to get executed, a program has to be loaded onto the main memory. However, what will happen if the size of the program exceeds the size of the main memory? And so you can see that a program can no longer be loaded onto the main memory if the size of the program exceeds the size of the main memory. So what should one do in such case? One possible solution is to divide the program into several components where each component is mutually exclusive to others. This means that there is no overlapping of instructions or data among multiple components. So we load the first component onto the main memory. Once it completes its execution, we can take it out from the main memory as the code or the data of this first component is no longer required. So now the second component can be loaded onto the main memory and it can complete its execution. In this way, one after the other, all the components can get executed. So this is the concept of overlays. Extending the concept of overlays, we have another interesting concept of swapping. As in overlays, we used to take out a particular component of a process which is no longer required. In swapping, we do the same for processes. So a process can be swapped out of the memory temporarily to a backing store, and after a while it can be brought into the memory to continue its execution. This may be required so that multiple other processes which are unable to get executed due to shortage of space, they can also get a chance to get executed in the presence of the same physical memory. So we can swap in a process and we can swap out a process from the backing store. However, a major downside of this swapping is the transfer time, as we have to copy some data from the main memory to the backing store, and on its way back when we are loading a process back to the main memory, we again have to copy the data from the backing store to the main memory. So the major time that is required for swapping is the time to transfer data and code from the main memory to the backing store and from the backing store back to the main memory. And we have to maintain some queues in order to have smooth execution of multiple processes that are present in a system. So over here we have an overview of this concept. So as you can see that we have this main memory. So a process can be swapped out of this main memory and being placed onto this backing store, while some other process can be swapped in from the backing store to the main memory. And this is how a fixed main memory can be utilized by multiple processes that may not be able to get executed in the presence of the same space. This swapping is a costly operation because a lot of time is consumed while we are copying the data and instructions from the main memory to the backing store and vice versa. So now let's combine this concept of swapping with the context switching that we discussed in earlier modules. So if the next process that is scheduled to put into the CPU is not in the main memory, so you may require to swap out a process from the main memory so that you can swap in your targeted process. So in this case, the context switch time can be very high. So for instance, if you have a process of 100 MB and the transfer rate is 50 MB per second, then the swap out time will be 2 seconds, which is 2000 milliseconds. And because you have to swap in the same size process, so you may require 2000 milliseconds more for swapping in. So the total context switch time, including this swapping, may be around 4000 milliseconds, which makes the whole thing quite costly. Alright students, so that is all for today. In today's lecture, we discussed the concept of memory management and saw why it is important for a program to be loaded onto the main memory so that it can get executed. Then we discussed the concept of address binding, a mapping between the logical addresses and the physical addresses. Now further, we discussed the concept of overlays and saw how a process that is larger than the size of the available physical memory can get executed in the system. And then by extending the concept of overlays, we discussed swapping, where processes can be swapped in and swapped out of the main memory at runtime. And then we discuss the concept of swapping with respect to context switching and its impact on the total time of context switching. All right, students, so please take good care of yourselves. Thank you.